You know when you strike a match and you get that sudden burst of light and heat? Ever stop to think about where that energy actually comes from? Well, in this explainer, we're going to dive right into the chemistry behind that little flame and uncover the incredible energy that's hidden all around us in plain sight.
So let's just ask that question, point blank. When you see that flame and you feel that warmth, is that energy just being created out of absolutely nothing? Well, the short answer is no, not at all. The energy was already there, the whole time, just stored away, waiting for the right moment to be released.
And look, this isn't just about a tiny matchstick. The principles we're about to cover are the exact same ones that power, well, our entire world. The energy released by chemical reactions is literally the engine that drives modern society. Just how much do we rely on this? To put it into perspective, data from 2012 showed that a staggering 85% of all energy consumed in the United States came from combustion. That's the chemical reaction of burning things like petroleum, coal, and natural gas. Just wow.
And you can see where all that energy went. 38% of it was just to generate our electricity, 27% to fuel our cars, planes, and ships. And the rest? Well, that powered our industries, our homes, and our businesses. It really touches almost every single part of our lives.
And you know, it's not all about setting things on fire. Think about the battery in your phone or in an electric car. It doesn't burn anything, right? But it's powered by the very same fundamental principle, unlocking stored energy from chemical reactions. Okay, so where is all this energy hiding? It's locked inside the connections between atoms, what chemists, of course, call chemical bonds. The key thing to remember is that energy isn't created during a reaction, it's just unlocked. Think of it like a two-step dance. First, you have to put some energy in. You need that initial spark to break the old bonds that are holding molecules together. But then, as new, more stable bonds form, a whole bunch of energy gets released out. The heat and light that we see and feel, that's just the net difference from this big energy exchange. And this brings us to a really core concept. A chemical bond isn't just some kind of atomic glue. As our source material puts it beautifully, it's another form of energy. It's a type of stored potential energy, just waiting to be transformed into something else.
And this isn't just an abstract idea. Scientists can actually measure this. It's called bond energy. It's the precise amount of energy needed to snap a specific bond. And because we can measure this, we can calculate the exact energy potential that's locked away inside all sorts of different molecules.
So this whole idea of energy in versus energy out lets us classify reactions into two main types. Basically, are they the kind that release energy and get hot, or the kind that absorb energy and get cold?
Right, so when a reaction releases more energy than it took to get started, it's called an exothermic process. Exo means out, think exit. So energy goes out. This is your campfire, the burning match, pretty much anything that gives off heat.
And the opposite of that is an endothermic process. Endo means in. These reactions actually need to pull in more energy than they release, so they suck heat from their surroundings, which makes things around them feel cold. That instant cold pack you use for a sports injury? Perfect example.
So, how do we keep track of this energy balance in a scientific way? Well, chemists use a concept called enthalpy. You can think of it as the official energy scorecard for any chemical reaction.
Specifically, we measure something called the enthalpy change, which is represented by the symbol delta H. This one value gives us the final score. It tells us exactly how much heat was either released or absorbed during the whole process. It's the bottom line.
And the calculation for this is actually pretty logical when you think about it. The total enthalpy change, that's our delta H, is just the total energy you spent breaking the old bonds minus the total energy you got back when the new bonds were formed.
And here's the easiest part, reading the final score. If that delta H value is a negative number, it means energy was released. It's an exothermic reaction. If delta H is positive, it means energy was absorbed from the surroundings. It's endothermic. Simple as that.
Now, this all makes sense in theory, right? But how do scientists actually measure this heat transfer out in the real world in a lab? Well, the process involves a special technique. That technique is called calorimetry. It's the precise science of measuring the flow of heat. Scientists use a device called a calorimeter to basically trap a reaction and measure the temperature change it causes. And these tools can be surprisingly simple, like the insulated coffee cup calorimeters you might see in a high school chemistry class. Or they can be incredibly sophisticated, like these things called bomb calorimeters, which are used for super precise measurements, like even figuring out the calorie content of the food we eat.
Okay, so let's bring it all home. The heat from that match isn't new energy.
It's old energy that was stored in chemical bonds, and it's just being transformed and released. This all follows one of the most fundamental rules of the universe, the first law of thermodynamics. Energy can change form, but it can't be created or destroyed. And that leaves us with a pretty fascinating thought, doesn't it? We've unlocked the energy in wood, in coal, and in oil. We've built these incredible batteries that power our entire digital world. So, if every single chemical bond out there is its own tiny little storehouse of potential energy, you just have to wonder, what powerful new reactions are out there, just waiting for us to discover next?